In this example, we're going to look at a water tank, and this time in the shape of an inverted cone. It says we have a water tank in the shape of an inverted cone with a radius of 2 meters and a height of 4 meters. If water is being pumped in at a rate of 2 cubic meters per minute, find the rate at which the water level is rising at 3 meters deep. So if you watch the cylinder video, it is the same dimensions, but it's a cone. Okay, inverted cone means ice cream cone. Point down. Okay, so we know that we're going to have a height total of 4 meters and a radius of 2 meters. Okay, so this is going to get filled with water. All right, so the volume of a cone is 1/3 pi r squared h. Okay, that's just a fact from geometry. All right, now, with the cylinder, we could plug our radius of 2 in, but think about slicing this. So slicing this horizontally, taking circle slices. Are the circles changing or staying the same? They're changing. So what that means is we cannot put that 2 in, and we can't put the h in either. So everything here is changing. So I've got 3 variables. Okay, well, we've got a problem. And that is with cones, we usually only have 2 rates at a time, meaning I'm given a volume and I want to know how the height is changing. So I have to somehow relate r's with h's. So what we're going to do is we're going to use a little bit of geometry. And what that geometry is similar triangles. So what I'm saying is that if I were to take a slice down here, right, and call it h and r, it's got to have the same proportion. So that little h and r that I just drew has to have the same proportions as the big one, which is 4:2. That's what similar triangles say. So what happens is that 2 is to 4 as r is to h, or that r is 1/2 h. And maybe some of you recognize that from the beginning, that yeah, 2 is half of 4. Okay, so what I'm saying is that that relationship between r and h of 1/2 h equals r will happen for the whole entire cone. It doesn't matter what level I'm talking about. That relationship has to still stay true. So what I'm going to do is I'm going to plug in that into this volume equation, okay? So where I see an r, I'm going to put a 1/2 h. Okay, so what I'm going to have is the volume equals 1/3 pi. 1/2 h squared would be 1/4 h squared times an h. So it looks like my volume equation will be 1/12 pi, or pi 12ths, and then an h cubed. Pi 12ths and an h cubed. Okay, now we're going to take the derivative with respect to time. dv dt equals, that 3 is going to come down. The 3 and the 12 will reduce to a pi 4ths h squared dh dt. Okay, now it's plugging in time. I got to figure out what goes in where. So I know that my water is coming in at a rate of 2 cubic meters per minute. dH dt is what I want to know. And in the previous video with a cylinder, we didn't have an h. It was just constant all the time, meaning when I took the derivative, the h disappeared. So there wasn't an h at this stage is what I'm saying. I have an h, so it matters. And hopefully that makes sense. If you've ever watched a cone fill up, it's going to fill up really fast at the beginning, or it's going to look like it's filling up really fast at the beginning because this volume is so small, but up here it's going to appear like it's slowing down because it's spreading out. Okay, so I want to know when it's 3 meters deep. So that's the moment that I'm interested in, is when h is 3. Okay, so I'm going to get 2 equals, let's see, 3 squared is 9, so I'm going to get 9 pi 4ths. So when I solve this, it looks like I'm going to get dh dt is 8/9 pi. Obviously, I'm kidding, it's not, I wouldn't have guessed 8/9 pi at the beginning. Okay, so what we would say is that the height of the cone 3 meters deep is changing at a rate of 8 over 9 pi, which is the same thing as 0.28 meters per minute. So there it is. That's our answer. Okay, so when you're playing with cones, couple things to remember. One is that we're going to use this formula. R's and H's are changing. You want to use similar triangles in order to relate R's to H's so that my equation is all in H's. And then finish it out. Bada bing. All right, good luck. I hope that went well.